Carbon numbers, they're non-negotiable. There are a couple of concepts in organic chemistry that I consider to be the non-negotiables. These are the skills you have to master, you have to know cold, you have to take for granted if you want to be an OChem ninja. One of them is drawing carbon numbers and mapping them onto new structures. The first aspect of this skill is just numbering the carbon atoms in the molecule. It doesn't matter where you start, it doesn't matter what direction you go, it doesn't matter if you use even numbers, it doesn't matter if you use prime numbers, you could use shapes for all I care. We just need to find a system of organizing these carbon atoms. You can even number things that aren't carbon if it helps. I don't care. As long as you get some kind of system that helps you number these carbon atoms, that's the first step. Numbering carbon atoms, you could almost think like a grounding technique. When you turn the page on the exam and you freak out because you have no idea what's going on, you can use carbon numbering as a Zen moment. Take a breath, number the atoms in the molecule, collect your thoughts, and then answer the problem. Do you have to number every atom in every structure ever for the rest of your life? No, not really. As you get better at chemistry, you may be able to skip over some of these steps, but as a beginner student, I would really recommend numbering all the carbons all the time. Just make it a habit. As you see a new structure in a new question, just go ahead and number the carbon atoms in that structure just so you have a baseline. The second part is to map those carbon numbers onto the product of this particular reaction. In the original structure, it didn't matter where we started or if we went right to left or left to right, but now that we have this carbon system, we want to map these carbon atoms directly onto their corresponding carbons in the product. I see the CH3 group that's next to the double bond that I've labeled as carbon number 1, and I see a similar structure in the product, so it stands to reason that this is also carbon number 1. The more similarities you see in these structural features, the easier it will be to map those carbons. That makes this double bond, carbons 2 and carbons 3, and the carbon at the top, carbon 4, and now we have an OH, and the bromine 5 is now over here. So in this reaction, whatever happened, it seems like oxygen interacted with carbon number 4, the bromine somehow left the molecule, and the oxygen is now attached to carbon 4 in its place. That's not the point of this. I have a separate video on SN2 reactions that I'll link to down below. This is just about numbering and mapping the carbon atoms. A lot of the times, the carbon mapping will be quite simple. The structures will look very similar, and it can be a nice check your work to make sure that you got the right atoms in the right places and you didn't drop or add or rearrange any carbon atoms. Let's take a look at this next example. Pause the video, go ahead and give the original structure a carbon numbering system, and see if you can map those numbers onto the corresponding product. Again, it doesn't really matter where you start, what direction you go, if you use even numbers or square numbers or Fibonacci numbers, it doesn't really matter. So you may have numbered a little bit differently than I did, it doesn't really matter. As long as you give the molecule some kind of numbering system, that is what's important. Now, let's map those numbers onto our product. I see these 3 CH3 groups here at the end of the molecule on the left side. So it stands to reason that these are the same CH3 groups as on the new product. That makes this carbon number 2, we have a carbon number 3, and it looks like this double bond is now gone, and there's a new single bond with a positive charge at carbon number 4. Why is this important? It gives us a language with which we can talk about these reactions. I can talk about the reaction at carbon number 4 now that I've given it a numbering system. Again, it also makes sure that I don't drop or add any carbons as I move from the starting material to the product. It's easy to drop one of those carbons on the right if you're not careful and not numbering your carbons. Non-negotiable. Have to know how to number the carbons and map them onto the product. Let's move to a little bit higher ninja level. Let's see if you can give these starting materials a numbering system and map those numbers onto the product. Pause the video, see if you can do that. Again, you may have a different numbering system than I do. It doesn't matter where you start or what direction you go in. We're going to use this time to collect our thoughts. Maybe we've never seen this reaction before. Maybe you're not even here in lecture yet. That's fine. We're going to use this time to figure out what's going on as we number these carbons. Now we're ready to map them over. If we want to, we can also number the oxygen and even the magnesium if we want to. We can number whatever we want. It's your system. You can number whatever you want. I see this benzene ring here that's also in the product. So I'm going to go ahead and call these carbons 1 through 6 again. That's going to help me map these carbon atoms into the new product. The rest of it doesn't quite look the same. The oxygen's on a wedge here, it's on a dash here, but what I do see, and this is an important part of mapping numbering systems, see if you can find something that's conserved between the two structures, a guidepost, a signpost, if you will, that helps you in your map. I see these 3 carbon atoms on this T-butyl group, 10, 11, 12. So these are likely 10, 11, and 12 here. Those are all connected to 9, and so that means 9 is connected to 8. Which is good because 8 was connected to the oxygen, and it still is. And now we have carbon 7. Carbon 7 is not connected to the oxygen anymore, but it is connected to carbon 1. So whatever reaction this is, looks like carbon 1 is now bonded to carbon 7, and somehow the 7 oxygen bond broke, but the oxygen is still attached to carbon number 8. This carbon number mapping system, even before you ever learn this reaction, gives you an idea of what kinds of transformations must be taking place. That's another reason mapping is such an important tool in organic chemistry. All right, let's up the ninja level even more. See if you can give this one a numbering system. This one's a tricky one. See if you can give the starting material a numbering system and map those numbers onto the product. Pause the video now, see if you can do that. I've gone ahead and given this starting material a numbering system. Again, you didn't have to do it the same way I did. We should still get to the same place, but this is how I numbered it. I even numbered the oxygens because I think it's going to be useful here. This is a tricky one to map onto. What I'm looking for is something that I can see conserved in both structures. That's going to be my map, my guidepost. And what I see that stands out to me is this isopropyl group 11, 12, and 13 in the starting material. I only see one isopropyl group here in the product, so that is going to be where I start. I'm going to call this central carbon 11, and this one 12, and this one 13. This is the isopropyl group from the starting material mapped onto the product. From here, it's a matter of following the carbons along. 11 is attached to 10, so this must be carbon 10. And that makes sense because carbon 10 is attached to an oxygen. Now, in the starting material, 10 is attached to 7, and 7 has this ethyl group attached. So when I think about mapping the carbons onto the product, 7 could be either one of these two. But this is the one that has the ethyl group attached, so this is likely to be 7, 8, and 9. 7 is attached to 6, which is attached to 3, and 3 has the ethyl group 4 and 5 attached, so that starts to make sense. 3 is also attached to 2, and that makes sense because 2 has an oxygen and 2 has an oxygen here. And then 2 is attached to carbon number 1. Where'd carbon number 1 go? Looks like it's this carbon here, and somehow it got wrapped around and attached to carbon number 10. Now that we have all the carbon numbers in place, we can look at the oxygens. Attached to carbon 2 is oxygen 14, so this must be oxygen 14. Looks like it used to be negative, now it's double bonded. And attached to carbon 10 is oxygen 15, so this must be oxygen 15. Looks like it used to be double bonded, and now it is negatively charged. By finding some guidepost that you can use to guide your way as you map the carbons is how you can unravel these numbers and make sure you're getting the right numbers in the right place in each structure. Carbon numbers, they're non-negotiable. When I'm in office hours with students and students are struggling to figure out how to draw the product of a reaction, one of the things I almost always do is that let's go ahead and number the carbons in this starting material and let's see if we can figure out where they're going to end up in the product. And that's usually enough to slow the student down, help them figure out what's going on, and help them draw the product. I can't emphasize enough how important numbering carbon atoms is just to get a grasp on what's going on. It also helps you see a little bit into the future. Even if you've never seen a reaction before, you start to have an idea of what bonds are being formed and what bonds are being broken, and that gives you a big head start in your mechanism.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists and see what you like. As always, don't forget to like and subscribe.